Welcome to another deep dive. And today we're going to be diving deep on a topic that's pretty fundamental to how science actually works: models. Now, you, as someone who's curious about knowledge and understanding, maybe even someone who's thought pretty hard about philosophy, you've no doubt run into scientific models all over the place. Like we all know about the DNA double helix or these big climate models that are trying to tell us what the future is going to look like. But what we want to explore today is like what makes these models so important for science, and what do like serious philosophers of science actually think about them?
Yeah. When you actually start looking into it, the sheer range of models that get used in science is really pretty amazing. You've got everything from inflationary models and cosmology when we're talking about the Big Bang Theory to evolutionary models in biology and agent-based models for social sciences. Economists use equilibrium models to understand markets, and that's just, the tip of the iceberg. Philosophers have come up with this whole kind of, well, I don't know if I want to call it a zoo, but a whole bunch of different types of models: probing, phenomenological, computational, developmental, explanatory, idealized, toy models, minimal models. Even some people talk about fantasy models. It can seem a bit overwhelming. But what we're going to try to do today is sort of bring some clarity to this fascinating world of models.
Yeah, for sure. Because, like, under the surface of all these different kinds of models, there are some really big philosophical questions. Like, we're going to be thinking about the semantics of models, basically, how they represent the world. We'll be digging into ontology, like, what kinds of things are these models that we keep talking about. And then there's epistemology, which is how we learn from these models and build explanations using them. So, yeah, get ready for a pretty stimulating conversation. We're going to be cutting through a lot of this complexity to show you some important insights about the power and maybe even some of the problems with this whole idea of scientific modeling. So, okay, let's dive in. And I guess the first thing we got to unpack is semantics, the whole idea of representation.
Right. So at a really basic level, a lot of scientific models are representational. That is, they're meant to stand in for some target system in the real world.
Hmm.
Think about the classic example of the billiard ball model of gas. You treat molecules as these little tiny spheres that are bouncing around and colliding with each other, or, maybe a scale model of a bridge that engineers use to test how a design is going to work. So the big question then is, what does it even mean for a model to represent its target? And that's a really tricky question. But for our discussion today, I think it would be good to go through some of the main kinds of representation that philosophers have talked about.
Okay, so one type that I think we all get right away is the scale model. Basically, you make a physical copy of the thing you're interested in, but you make it bigger or smaller. It makes me think of those wooden models of airplanes that they put in a wind tunnel to like study how the real plane is going to fly. At first, you might think, well, those are pretty simple. They're just like smaller versions of the real
Yeah.
thing, right?
Yeah, that's sort of the intuitive idea. But when you actually think about it more carefully,
Hmm.
you realize that perfect faithfulness is like kind of impossible to achieve. The wood airplane has the same shape as the real one, but it's obviously not made out of the same materials. And even for those aspects that the model does get right, the relationship between, say, a length in the model and the corresponding length in the real airplane isn't always simple. It's not always just like multiply by 10 or divide by 100. So when we use models to understand the real world, we have to be conscious about like taking results from the model and directly applying them to the real thing. Sometimes it's more complicated than that.
Yeah, definitely. Like a good example of that is when you use a model of a ship to study how much resistance it's going to have when it moves through water. Let's say you build a model that's 1.10 the size of the real ship. You can't just take the resistance you measure on the model and multiply it by 100 to figure out how much resistance the real ship is going to have. It's not that straightforward. The relationship is often nonlinear. And you actually have to like do a lot of research to even figure out what the right relationship is.
Right. And then you've got analogical models, which are models that work by drawing a similarity between the model and the target. Again, the billiard ball model of a gas is a good example here.
Yeah.
You're saying that gas molecules are like these tiny little hard spheres bouncing around.
So it's all about making these deliberate comparisons, right? And there are like different types of comparisons you can make.
Totally. The philosopher Mary Hess did a lot of work on analogies, and she said there are analogies that are based on shared properties, like the Earth and the Moon. They're both big, roughly spherical. They both rotate, right? But then you've also got analogies based on similar properties, like sound and light are often compared, and there's an analogy there where echoes are kind of like reflections, and loudness is similar to brightness.
Right. So it's not that they're exactly the same. It's more like they have these comparable features that make the analogy work.
Exactly. And then you can also have analogies based on similar relations. Like you can compare the relationship between a father and his children to the relationship between a state and its citizens. That's a classic analogy.
Mm.
And has also made this distinction between material analogies, which focus on these kind of concrete features and relationships, and formal analogies.
And I guess formal analogies are more about the abstract pattern or structure. The details kind of fade away, and you're left with this underlying, like, mathematical form, right?
Yeah, exactly. It's when you can describe both the model and the target using the same mathematical structure, the same equations. Like the classic example is a swinging pendulum and an oscillating electrical circuit. They're both described by the same kind of differential equation, so they're formally analogous.
Okay, so there are all these different types of analogies, but how do they actually help us in science? How do they move us forward?
Yeah, so Hesse also came up with this idea of positive, negative, and neutral analogies. The positive analogy is all the stuff that the model and target share. The negative analogy is the things that we know are different between them. And then the really interesting one is the neutral analogy. That's all the stuff where we don't yet know if the model and target are similar or different. And it's this neutral analogy that can lead to new research questions, new things to look into. It's kind of where the generative power of analogies comes in. So it's not just about looking at what we already know is similar. It's about using the analogy to figure out what else might be similar.
So it kind of drives scientific inquiry forward. Now, there's also this question of whether analogical models can actually provide like real confirmation for our scientific ideas.
Right, and that's something that philosophers are still debating. Hess thought that material analogies could be confirmatory, especially in a Bayesian framework, where seeing a predicted similarity can increase our confidence in a hypothesis. But some philosophers, like Paul Bartha, disagree. They say that often the information contained in the analogy is already part of our background knowledge, so seeing the analogy play out doesn't really give us any new evidence that should change how confident we are in a hypothesis. He says maybe analogies can establish plausibility, which means that the hypothesis isn't totally crazy to begin with, but they might not provide actual confirmation.
And this debate has actually become even more relevant recently because of this whole new area of analog experiments, where they're using things like dumb holes in fluids to try to understand how black holes might behave.
Exactly. So the idea is you can maybe use one physical system to learn about another system that's really hard to study directly. Like, can we really learn about black holes by studying these fluid analogs? And specifically, can we get evidence for things like Hawking radiation, which is supposed to be emitted by black holes, by looking at these analogs? It's a really hot area of research right now with a lot of debate about how and when these kinds of cross-system confirmations might actually be possible.
Fascinating. Okay, let's keep moving. So another type of model that's super common in science is the idealized model. This is where you simplify things or even distort reality a bit to make the system easier to analyze. So scientists make strategic choices about what to leave out or even what to get wrong, not because they're like ignoring reality, but to make the problem solvable and to really see how the core mechanisms are working. But I guess the trick is knowing what you can get away with simplifying, right?
Right, for sure. Like in physics, you have the classic examples of frictionless planes or point masses, and in economics, you have perfectly rational agents. These are all idealized models. They let us grapple with systems that would be just way too complicated to study if we tried to include all the messy details of the real world.
And philosophers have made this important distinction between different kinds of idealization, haven't they?
Yeah, so one really important distinction is between Aristotelian and Galilean idealization. Aristotelian idealization is about stripping away properties that we think are irrelevant to the problem at hand, so you just focus on a few key features. Some philosophers say this doesn't necessarily involve making false claims. It's more like you're just not saying anything about those other aspects. Like if you're building a basic model of the solar system using classical mechanics, you might focus just on the positions and velocities of the planets and ignore things like their color or what they're made of.
So it's kind of like you're choosing to pay attention to certain things and ignore others. And Galilean idealization is different.
Yeah, Galilean idealization is more about deliberately introducing distortions. You're putting features into your model that you know aren't perfectly accurate, but that make the problem easier to solve. That example of the frictionless ice rink is a classic case of Galilean idealization. Galileo himself used this kind of idealization all the time to simplify physical problems so he could analyze them mathematically.
And sometimes people talk about these Galilean idealizations as being controlled, meaning that in theory, you could later go back and remove those distortions to get a more realistic picture, right?
Yeah, that's the basic idea. But some philosophers have argued that not all idealizations are like that. Some idealizations are kind of baked in. You can't just remove them without the whole model falling apart.
Hmm.
You see this a lot in modern physics with some of the very abstract models they use to study things like elementary particles.
So how can we actually learn anything about the real world from these idealized models, especially if they're like deliberately inaccurate?
Yeah, that's a great question. So the philosopher Ronald Layman came up with this idea of thinking about idealizations as ideal limits. The basic idea is that if you can imagine a series of increasingly realistic scenarios that kind of get closer and closer to your idealized model, and if the behavior of those more realistic systems keeps getting closer to the behavior of your ideal model, then maybe studying the ideal limit can actually tell you something useful about real systems, even if those systems never perfectly reach those ideal conditions.
That makes sense. But there are also cases where taking these limits can lead to weird results, right?
Exactly. You can have what are called singular limits, where the behavior of the system at the limit is totally different from the behavior of systems that are very close to the limit but not quite there. This happens in a lot of different areas, like in the study of phase transitions, and it makes you wonder how to interpret the results you get from these idealized models. Some philosophers think these singular limits are pointing towards, like, emergent phenomena, while others say they're still compatible with a reductionist view of the world.
And it seems like in practice, a lot of scientific models probably use a mix of both Aristotelian and Galilean idealization, right? They pick out certain features to focus on and then simplify or distort others to make the model work.
Exactly. Like, think back to that model of the solar system using classical mechanics. It focuses on just a few properties like position and gravitational force, but it might also treat the planets as perfect spheres, which of course they're not. Now, one thing that people often confuse with idealization is approximation.
Right, like when you say one number is close to another number.
Yeah, in a general sense. But some philosophers, like Roman Frigg and Stephen Hartman, make a distinction. They say approximation should only be used for cases of quantitative closeness. So you can say that one mathematical curve is an approximation of another curve if there's a well-defined sense in which they're numerically close. Like if you're using a simpler polynomial to represent a more complicated curve, you might say that the polynomial is an approximation of the real curve.
Okay, so how is that different from idealization?
So John Norton argues that the key difference is what the description is of. An approximation is an inexact description of the target system itself. But an idealization is when you introduce a second system that's distinct from the target system, even if it's based on the target system. Like if you say that the period of a particular pendulum is approximately 2 seconds, that's an approximation. But if you say that the pendulum behaves as if it's a point mass hanging from a massless string, that's an idealization because you're introducing this idealized pendulum that doesn't really exist. Of course, you can often justify approximations by appealing to idealizations. Like, the reason we can approximate the period of a real pendulum is because we're assuming it behaves like this idealized pendulum.
Okay, so we've got a pretty good handle on the different ways that models can represent things in the world. What about toy models? I feel like the name itself suggests that these are like simplified and maybe even playful representations.
Yeah, that's a good way to think about them. They're very simplified, often highly distorted versions of the systems they're trying to represent. And they usually only include a very small number of the most important factors. Like the Luck-Volterra model in ecology is a classic example of a toy model. It tries to describe how predator and prey populations change over time, and it does it using just a couple of differential equations. Or in social science, you have the Schelling model of segregation, which is another example of a toy model.
So I guess you wouldn't use them to make super precise predictions about what's going to happen in the real world. What are they good for then?
Yeah, so they're often used for different purposes, but they can still be really valuable. They can help us understand basic mechanisms or explore different possibilities. They can even provide, like, existence proofs, which means they show that a certain kind of behavior is at least possible. But this raises an interesting question for philosophers, like, if they're so simplified and distorted, should we even think of them as representing anything at all?
And sometimes these toy models are called caricature models. I'm thinking of George Egerloff's famous market for lemons model in economics, which is a really good example of a caricature model.
Right, so caricature models take a few key features of the system and they exaggerate them, often to an extreme, while ignoring other factors that are obviously important in the real world. Like Akerlof's model tries to explain why used cars are cheaper than new cars by focusing almost entirely on the fact that sellers usually know more about the quality of the car than buyers do. So the question is, can these super simplified models actually tell us anything useful about the real world?
And then you have minimal models, which sound even more stripped down than toy models.
Yeah, they really are. And some philosophers argue that they're so simplified that they're not really representing anything anymore
Yeah.
in any kind of straightforward way. Like they might not resemble the real world systems they're supposed to be about in terms of their structure or their features.
Mm.
And some people say a lot of economic models are like this. They're not constrained by like laws of nature, and they might not pick out any real causal factors that are operating in the world.
So if they're not representing anything concrete, how can they be useful for scientists?
That's the big puzzle with minimal models. The people who like them say they can still act as surrogates. So you can learn something about a real system by studying a minimal model, even if the model isn't directly representing that system. One idea that people use, especially in physics, is this notion of universality classes. So the idea is that different physical systems can belong to the same universality class if they show the same kind of behavior under certain conditions, even if they look totally different at a microscopic level. And a minimal model might be able to capture the behavior of a whole universality class, even if it doesn't share specific features with any particular system in that class. But this idea of universality is definitely controversial among philosophers.
Okay, interesting. What about phenomenological models? It sounds like these are models that focus on what we can actually observe.
Yeah, that's one way to define them. Basically, they're models that are mainly concerned with the observable properties of the system and don't try to say anything about the underlying mechanisms or causes. Another definition that people use, which comes from Ern and McMullen, is that phenomenological models are independent of any particular scientific theory. But a lot of people think that's too strict because a lot of phenomenological models do actually use ideas from different theories, even if they're not totally derived from any one theory. Like the liquid drop model of the atomic nucleus is a good example. It uses ideas from both hydrodynamics and electrodynamics to explain some things about how nuclei behave.
So they're basically saying what happens without necessarily explaining why it happens at a deeper level, right?
Often, yeah. And they're also related to this idea of models of a phenomenon, which are models that try to capture general features of how things work in the world, like the fact that sound gets weaker as you move farther away from the source.
And then there are exploratory models, which sound like they're kind of like the first drafts or sketches in a scientific investigation.
Exactly. They're not meant to be definitive explanations of anything specific. They're more like starting points that you can build on and refine later. They can provide what people sometimes call how possibly explanations, or they can show that a certain kind of thing is possible in principle. Like those early models of population growth in ecology, the Lotka-Volterra model again, are a good example. They're not trying to accurately describe any particular population, but they're showing that population growth could happen in a certain way. They can also tell us about what's possible, which is what Michele Massimi calls modal knowledge. And they can also be useful for figuring out what a particular theory actually implies or predicts.
And finally, we have models of data. It seems like this has to do with how we handle all the raw information we get from experiments and observations.
Yeah, definitely. A model of data is like a cleaned up, corrected version of the raw data that you get from doing an experiment or making observations. It involves things like getting rid of errors, which is called data reduction, and fitting mathematical curves to the data, which is called curve fitting.
So it's about taking the messy measurements we get from the real world and making sense of them.
Right. And these models of data are super important for testing scientific theories, because when we test a theory, we're actually comparing it to a model of the data, not to the raw data itself. And building these models of data can be really complicated. It involves using all sorts of statistical techniques, and it raises a lot of philosophical questions about which data points you should throw out and which mathematical function is the best fit for the data. So it's not just about collecting the data, it's about doing all this work to process it and make it useful.
Okay, so we've got a good grasp of all these different kinds of models that scientists use and the different ways they can represent things. Now let's switch gears and think about the ontology of models. Like, if we wanted to put models into categories, what kinds of things are they?
Yeah, this is something that philosophers of science have been arguing about for a long time. Some philosophers even say that models don't form a special category at all. They say that pretty much anything can be a model depending on how you're using it.
So, like, a real physical object could be a model or a set of equations or even a thought experiment.
Exactly. But another philosopher, Gabriel Contessa, argues that even if there are lots of different things we call models, it's still worthwhile to think about the different kinds of things that get used as models. Like understanding what those things are can tell us something about how they work as models and what they can do.
So, what are some of the main categories that scientific models fall into?
Well, one obvious category is physical objects. We sometimes call these material models, like those scale models of bridges and ships we were talking about earlier, or the physical model of DNA that Watson and Crick built. Those are all real physical things that are acting as models for something else. And from a philosophical perspective, they don't really raise any new problems. They're just physical objects like any other.
But like we were saying before, a lot of important models aren't actually physical objects. What about those?
Yeah, so that brings us to the categories of fictional objects and abstract objects. There's this idea called the fiction view of models that's become pretty popular. It says that we should think of scientific models as being kind of like the characters and things we find in fiction, like Sherlock Holmes and the stories by Arthur Conan Doyle. So the idea is that when Niels Bohr came up with his model of the atom, he was basically creating a fictional object, just like Conan Doyle created a fictional detective.
That's a really interesting way to think about it. And it kind of fits with how scientists talk sometimes. Like they'll talk about imaginary atoms or populations that don't really exist.
Yeah, it does. And Roman Frigg, who's one of the people who's worked on the fiction view, says that this comparison to fiction is actually really helpful because philosophers who study fiction have already thought a lot about the same kinds of questions that come up with models, like what makes a fictional character or object the thing that it is? What properties do they have? What does it mean to say that one fictional object is similar to another? And even how do we learn about these fictional worlds? So maybe we can learn something about models by looking at what philosophers of fiction have figured out.
So we can kind of borrow some insights from how we understand fiction to better understand how models work.
Exactly. So Gabriel Contessa has this idea that a model is an abstract object that stands for a possible real object.
Mhm.
And other philosophers like Anouk Barberousse and Pierre Ludwig and Roman Frigg again have developed accounts based on something called the pretense theory of fiction, which was developed by Kendall Walton. So the idea here is that when we talk about a model, we're engaging in a kind of game of make-believe. The descriptions of the model are like the props in this game, and the model itself is what we imagine when we're playing the game. So this view is kind of anti-realist. It's saying that the objects we talk about when we're talking about models don't really exist outside of our imagination.
But there's also a more realist version of this fiction view, right?
Yeah, so Andreas Snatlis has this idea that she calls the new fiction view. And she says that the model isn't the act of imagining itself, it's the content of what we're imagining. And since those contents exist in some sense, this is a way to make the fiction view more realist.
And it seems like a lot of philosophers of science have criticized the fiction view. Like one worry is that calling a model fiction might make it sound like it's just totally made up or false, which
Uh,
isn't really how we think about models in science.
Yeah, that's a common criticism. The worry is that it makes it sound like models don't have any real value or that we can't learn anything from them. Just because a model makes some simplifying assumptions or idealizations doesn't mean that the whole model is useless or that it can't tell us something about the real world. And the people who defend the fiction view usually say that fiction doesn't have to mean false. They say that the important thing about fiction is that it invites us to imagine things, not that the things we're imagining are necessarily false.
Okay, so what about this other idea that models are abstract objects?
Yeah, Ronald Gere has been a big defender of that view. But of course, the whole idea of abstract objects is a really complicated issue in philosophy, and there are a lot of different views on what they are. And more recently, Amy Thomason and Peter Thompson-Jones have developed this idea called the artifactualist view of models, which tries to find a middle ground between the pretense theory and realism. So they agree with the pretense theorists that we often engage in a kind of pretense when we're talking about models, but they say that when we do this, we're actually creating abstract cultural artifacts that exist independently of us. So this is a kind of realism, but it doesn't require us to believe in like a Platonic realm of abstract objects.
And then there's this other view that's been really influential, especially among philosophers of science, which says that models are basically sets. This seems connected to that idea of the semantic view of theories that we talked about earlier.
Right, so this view comes from the work of Patrick Sapis, and it says that scientific theories aren't really about statements or axioms. They're about models. And these models are understood as sets, which are just collections of objects, along with some relations between those objects. This view has been really influential, but it's also been criticized. Some philosophers say that a lot of important scientific models just don't fit this framework very well. And they say that even when they do fit, you still need to add more interpretations and descriptions to connect the model to the real world.
And then there's the more traditional idea that models are descriptions and equations. Like they're just ways of describing a system in a simplified or stylized way.
Yeah, this view has been around for a long time, but it faces similar problems to some of the older views of scientific theories. Like, it's hard to say when two descriptions are actually describing the same model, and it's also hard to explain why a model can have properties that aren't mentioned in its description.
But I thought there were some people who still defend this kind of view.
Yeah, there are. So Arnold Levy and Adam Toon have developed something they call the direct representation view, which is based on Walton's pretense theory, but in a different way than the standard fiction view. They say that there aren't really any models that are separate from the real world. They say that modeling is just about giving imaginative descriptions of real things. So like the idealized pendulum isn't as a separate thing, it's just a way of imagining a real pendulum. They're trying to get around some of the problems that the older versions of this view had, but it still raises some questions, especially when you're talking about models that don't have any clear real-world target or that involve really heavy idealization. And the view that models are just sets of equations has similar problems. Like, you can have different equations that describe the same model, and models can have properties that aren't directly captured in their equations.
Okay, so that gives us a good overview of all the different ways that philosophers are thinking about what models are. Now let's move on to epistemology. Like, how do we actually learn things from models and use them to build explanations?
Yeah, this is where models really become important in science. Models let us do all sorts of things that we wouldn't be able to do otherwise. Susan Sterrett says that they're vehicles for learning, and Ronald Sawyer famously said that they allow us to do surrogative reasoning. So the idea is that we study the model, we do experiments on it, either real experiments or thought experiments, and then we use what we learn about the model to learn something about the real world. Some philosophers even say that this is a special kind of reasoning called model-based reasoning that's central to how science works.
So instead of studying the real world directly, we can often learn more by studying a model. But how does that actually work?
So Mary Morgan says that learning about a model happens in two main stages. First, you build the model, and then you manipulate and analyze it. And just figuring out how to put the model together and how the different parts of it fit together is a learning experience in itself. And then once you have the model, you don't just look at it passively. You poke and prod it, you run experiments on it, you tweak its parameters to see how it behaves under different conditions. That's how you really start to understand what the model can tell you.
And the way you learn about a model probably depends on what kind of model it is, right?
Oh, absolutely. If you have a physical model, you can do experiments on it just like you would with any other physical object. But if you have a fictional or abstract model, then you have to use different tools. And one of the most important tools is the thought experiment. And philosophers have had a lot to say about how thought experiments work and what kind of knowledge we can get from them.
And now that we have powerful computers, computer simulations have become a really important part of how we learn about models, right?
Yeah, they really have. Computer simulations let us explore what happens with models that are too complicated to solve with just math. Like, we can simulate all kinds of things now, from how galaxies form to how diseases spread through a population. And they're also really useful for coming up with new ideas and hypotheses because you can explore a huge range of possibilities with simulations.
But we have to be careful about how we interpret the results of simulations, right?
Oh, for sure. Simulations can sometimes be misleading, like if you're not using the right parameters or if the simulation itself is oversimplified. And now that computers are so powerful, there's a temptation to build models that are too complicated too early, which can lead to models that fit the data really well but don't actually tell you anything useful. And you also have to be careful about whether the simulation itself is working correctly. Like, are the algorithms doing what they're supposed to be doing?
So let's say you've learned something from studying your model. How do you then apply that knowledge to the real world, to the thing that the model is supposed to be representing?
Yeah, that's where the representational function of the model comes in, the stuff we were talking about before. If the model actually does represent the target system in some way, then what you learn from the model can potentially tell you something about the real world. But how that knowledge transfer works depends on how the model is representing the target. Like, if it's an analogical model where the relationship is one of similarity, then the way you apply the knowledge is going to be different than if you have a model that you think is a more realistic depiction of the target. And it's even more complicated if the model involves idealizations.
Now, one of the big things that models are supposed to do is provide explanations. But how can a model that's idealized or maybe even deliberately inaccurate actually explain something in the real world? That seems kind of strange.
Yeah, that's a really big question in the philosophy of science, and there's a lot of debate about it. Traditionally, a lot of philosophers have said that a good explanation has to be based on things that are true, or at
Hmm.
least approximately true. But that doesn't really fit with how we use models in science, because models often include things that we know are false. Some philosophers who like this traditional view say that the idealizations in a good model don't really matter for the explanation. Or they say that good models are at least approximately true, and you could, in theory, get rid of the idealizations to get a more accurate model without losing the explanatory power.
But some philosophers go even further and say that models can sometimes explain things precisely because they're false.
Right, so Nancy Cartwright, who's a very well-known philosopher of science, has this famous line, "The truth doesn't explain much." And she has this view called the simulacrum account of explanation, where a model explains something if it fits that phenomenon into a broader theoretical framework, even if the model itself isn't strictly true. And other philosophers have pointed out that even models that are false can still be really useful for eventually getting to a true theory. Like Wendy Wimsatt has talked about how models in genetics that are deliberately false can still help us understand more complex and realistic situations. And Roman Frigg and Adam Toon have even connected the explanatory power of some models to their fictional nature. They call them explanatory fictions. And then there are other philosophers who have non-representational accounts of explanation, which means they think models can explain things without actually representing anything in the world. It's a really active area of research right now.
Another big goal in science is understanding. Like, how do models help us to understand the world around us?
Yeah, a lot of philosophers of science now say that understanding is one of the main things that science is trying to achieve, maybe even more important than prediction or explanation. And this understanding can be about a particular phenomenon or a theory or even a whole area of science. And models are really important for building this understanding. Lord Kelvin, who was the famous physicist, once said that the ultimate test of whether you really understand something in physics is whether you can build a mechanical model of it. So the idea is that if you can represent something with a model, that means you understand it in a deep way.
So, building a model is a sign that you've really grasped something. But how can a model that's false or idealized help us to understand something? That seems a little counterintuitive.
Yeah, it does. But Catherine Elgin, who's another philosopher of science, has argued that false models, which she calls felicitous falsehoods, can actually be really important for understanding. She says that understanding isn't just about having true beliefs. It's about having a coherent and well-connected set of beliefs that lets you make good inferences. And models, even if they're not strictly true, can help us to build that kind of understanding.
And there's also a debate about whether understanding always requires having a